better there. Yeah. So good evening, friends. We come to the last session. This is more or less a debriefing kind of a session. It's brief, and we want to compare and also encourage why you should consider MicroSim as a viable alternative to do microstructure simulation. So whenever it comes to comparisons, one thing that comes to my mind is a question that somebody posed to me. Is it better to eat with a spoon or fork? So you can say, spoon can hold liquid stuff, and then you can say fork can twist around the spaghetti and all that. But the best answer for that question is that it depends on what you want to eat. The same thing is also applicable for these tools, for that matter, any tool. So which tool is better? The answer is actually what do you want to do with that? So I want to show that you can actually do a lot with MicroSim and then leave it to you what you should use it for. Okay, so in the last 2 days of workshops, we have got MicroSim's features shown to you. We have got several updates from the first version released about 6 months back. And so you would have seen that there are features that are typical of any open source software, namely, we don't actually decide how you should actually go about using these tools. So keep it as open with as many options as possible. So there are people who are fans of finite difference method. There are people who vouch for finite volume methods and spectral methods and so on. So all of them are available. And then there are those who feel that CPU is always reliable and should be the one which you should use for computation. Then there are some who feel that GPU is a better way because more computation per dollar of investment and all that. So all those options are also there. And then one major upgrade is that we have ability to look at the commercial databases so that real alloy systems can be modeled. So the CalFAD input is one big update now. And another big update is about the GUI tool. You have seen a number of features. You could actually go around and see how that compares with other tools that are in the market. So you will see that. And though we have made some initial files for both properties as well as the geometries, the so-called in files for specific problems, which are directly useful for casting, heat treatment, welding, etc., including additive manufacturing. But technically, you could use it as per how you would imagine for any metallurgical process, but even materials processing. So we can actually elaborate on those case studies as we go along, and we use this tool more extensively. So this is again talked about by Abhik yesterday, where this overall feature of how thermodynamic data got integrated in this second version. So here I want to bring to your attention. So if you look at the commercial tool like Micress, it's not like if you buy Micress and you can start using the commercial databases and start simulating. You actually need to also buy the TQ interface. You should buy the thermocalc engine, and also you should buy a license for the thermodynamic database. So you should have actually 4 licenses in place, and they will have certain compatibility issues, and one should have all of them updated so that you can actually use the capability. There are developments on Pandat also where the phase field simulations are coming up. Pandat is a strong competitor to thermocalc. And both of these have API calls available. In the past, Pan API was limited to only Visual C++ on Windows, but now I think it's open for Linux environment also. Thermocalc had only a Fortran interface in the form of TQ, but now it's a C++ API which is available on multiple platforms. So both of these commercial tools have made the data visible to us even through suspense is too much. It's not common, right? We don't have power cuts. No. Usually we don't have, right? Power cuts. We have. Have. start on your
No, this guy has switched.
No, that will start.
Because I think
No, but net is also gone. Switch to some other network.
the screen is still shared. Hey, link is still working.
Okay. Can you speak?
Yeah.
Hello?
So can we just see if you are able to hear me now?
Yeah.
Okay, good.
Yeah.
So sorry for the brief interruption. We had a power cut here. So just a recap of how the thermodynamic data is getting integrated to the second release of MicroSim. So we now have a program which would look at the unencrypted databases as well as extracted data from encrypted databases and process them so that the input is made available to MicroSim. You have got the function numbers PF is equal to 234 to take these options. Now, what it does is this sequence of steps is already illustrated to you. So we have now the possibility that if you can find a TDB file from a journal, then you could start actually working with that thermodynamic data for your simulation. So this is very different approach than having to depend on only those which are assessed and integrated into databases by commercial vendors, because they wouldn't actually have all the TDBs actually integrated. They would actually let you also use TDB files as input. So we have the same capability. So that is something that is very useful. Where do you find these unencrypted database files is something that I want to just say a word or two. So there's this journal, Alpha journal, one of the few where the thermodynamic data after assessment is published. So most of the publications would actually come with a TDB file that you could download. And so that is one good place to look for. And then NIST maintains a list of all these TDB I'm still connected.
No, you're still connected.
I'm still connected.
The network, it might have switched to the weak network.
No, it's still, don't change anything.
IAC WLAN. First one, right?
Yeah.
Yeah, we I think we're back to normal. Okay, so let us wrap up soon. There seems to be a lot of glitches with power here. So these slides are also.
Presenting.
Yeah.
It's presenting, but again there is some glitch. Wait. Go back to Teams.
No, it's visible on Teams.
Yeah.
Sometimes.
Huh?
It's there.
Okay. Now it came. No, but your voice is not there. Can you speak again?
Yeah. Can you hear me?
So for Teams we are using the mic
I
from
can see,
this.
I can hear you.
No, are you hearing me through the Teams?
Yeah.
Okay.
Of course.
How come?
I can hear you.
Okay, if we confirm.
Okay, let us do this soon.
You're audible.
So yeah, so here is a list of websites where you could pick up these TDB files. So we have these slides made available for you through the website of MicroSim. So we can go and serve those locations. And so some of the dependent information is something important to look at. So commercial TDBs are always upgraded. So which means that if you don't upgrade, then very soon some of your work may be not relevant. So it's important to actually keep paying for these upgrades just to be able to use these databases, because the versions are also then dependent on the engine. So the latest engine may not support too old a version of database, and vice versa. The latest database may not be supported with old engine. So one has to keep paying for all these version upgrades. One has to remember that. So the cost of the annual maintenance contracts and upgrades, just simply to have a continuous availability, is something that one has to watch out. And many of these datasets are actually going along with scientific publications. So we have to understand that if people can start putting the TDB files along with their scientific publications, then actually it ensures that everybody can use the data forever later on. So that's an advice for those who are doing thermodynamic assessment to make things visible for people. So one case study that we want to just show you to compare how MicroSim and Micress would work. So for this, what we have done is we have used the same TDB file and same domain and the same time step and so on, so that the simulations are actually as close to each other as possible. And it's a free dendrite growth problem that we have looked at. So here is the outcome. You could see that the superposition of the dendrite profile after the same amount of number of iterations is shown on the left top. On the right, you have got the concentration field, the MicroSim and Micress. If you did not have the labels, maybe you would not be able to distinguish between those two images. And the sidearms is a matter of random noise, which is not the same even if you do it 2 times in the same tool. So do not worry about minor differences away from the tip. But near the tip, the paraboloid shape is what is very important. So the curvature, the tip position are very important, and they are the ones which benchmark the microscopic scalability criterion being obeyed by these calculations, and that's benchmarked across models already. Yesterday we have shown, and then now across the software, Micress as well as MicroSim. So this, I would say, is like tour de force, saying that we are able to benchmark our free and open source software with a commercial software. Okay, and the in files for you to run these two, if you have access to both of them, will be made available to you, so that you could actually check this out yourself when you like to do it. Okay, so some features that are similar is something that you should know. So Micress would actually have a script file generated if you just want to store what is there on the command line as you start the Micress. And we also have a script file which is a little bit more organized, because it's not a capture of what is at the command line, but actually created in file. And so in a way, the initialization file for the software is a text file in both the cases. And then you could compile Micress for Windows operating system and run it. And Micress is also available for both. So in a way, both the softwares are available for multiple platforms, particularly Windows and Linux. Both the softwares can actually write their output files in VTK format. In fact, Micress would do it only for VTK, which is what we can use for in open in ParaView to do some further calculations. But MicroSim actually would export also to HDF5, which later you can convert to VTK and then do various calculations. And as you know, HDF5 is a more modern version of the data storage formats. So in a way, what is common is definitely quite useful across VTK format is available. And just a session before mine is a session on post processing, where you have seen umpteen number of metrics that you can export out of a simulation run. And that is also something that you could see, particularly the so-called virtual EDAX pattern that is extracted from Micress. We have that capability already. And of course, there are a lot more metrics that we can do from the outcome. Okay, and needless to say, we can always use ParaView to do the visualization and do any metrics. If you have a VTK file, doesn't matter whether it is from Micress or MicroSim, you can use ParaView to do whatever you want on top of it. So there are a lot of similarities, and therefore one should believe that these are actually having very similar capabilities. There are certain challenges that would also show you in what context Micress actually would not be able to serve you, and MicroSim could actually help you, particularly in terms of live coupling. You know that the thermodynamic databases come with license restrictions, which may not be possible in a HPC environment. Okay, because HPC environment has its own private LAN, which is disconnected from the campus LAN in most of the university settings. Whereas those may not be compatible with the license node IP addresses given meant for let us say thermocalc or Micress. And therefore this incompatibility means that if you want to submit a job which would run on any random node in the HPC environment, to get that IP address and then get the license checked out to do those calculations will just become actually impossible. So therefore one cannot use these commercial tools with IP restrictions in a HPC environment. Second big challenge would be on a scalability with respect to a single task. So we have seen from our experience that typically more than about 8 cores, the scalability is quite limited with respect to Micress. We would have to correct ourselves if there are any updates on that, but we are very sure about the scalability of MicroSim. Abhik Chaudhary has already shown about 4,000 cores we have been able to scale, and then even more than that later on. So when you want to do a run very quickly, in about half an hour you want to finish the run and you have all the computation that you would like, then nothing can beat the scalable aspect of MicroSim, because we have done the analysis and ensured that the scalability is available with you. Now, scalability of multiple tasks is also something that many people don't pay attention. That is, let us say you want to do a parametric study and you want to do 100 different runs and then analyze all the data. What happens is that there is a license restriction also. How many licenses can you check out at any given time? So how many jobs can you run is also something that you have to know. So if you run a Micress job, how many licenses are checked out depends upon how many cores it is running on, and therefore it will be limited by what license you have. So if you have a single license or a site license or 100 licenses, all of that actually tell you how many tasks can you run simultaneously. But because the MicroSim is actually free and open source software, so you can run as many jobs as you have the computer facility with you. So which means that there's a scalability across multiple tasks also. Now the statement I made about license restrictions for number of multiple tasks and scalability is not limited only to Micress, it's also for Abacus and ANSYS, etc. Everywhere you do have a payment per license, and in all those circumstances, you have this problem of how many tasks can you run simultaneously. And our own experience has shown that 3D multi-phase microstructures are quite painful with a commercial software that cannot scale above 8 cores, is because then it would almost take about a month to make a reasonable simulation on a desktop computer, which actually can be done in a couple of hours on a HPC environment using the MicroSim. So this is something that you should just definitely try out yourself and then come back and tell us if we were right. And then of course, when you look at what is the total cost of single simulation, by knowing what is the total investment on the licenses over 1 year, and then add to that workstations that you need to pay for, and then the power that you have to spend on, and the air conditioning, etc. If you add all of them for 1 year and then divide by the number of runs you can actually make, then you will get how much does it cost for a single simulation. And this is something that you can actually go and punch your numbers, and definitely you would come to a conclusion that is obvious. So some concluding remarks. So I think when it comes to 2D multiphase microstructure evolutions, I would say MicroSim is very, very comparable with Micress. We have actually done that to show you, and we'll be happy to do that for any other case study that you may want to check it out. Industrial alloy systems is not a limitation for us, because in this version we are able to handle that. And there is something that is very definitely not possible at all with Micress or other such tools is MPI plus GPU computing, where the solvers are accelerator ready. I'm using a very generic word called accelerator because CUDA via HIP or OpenCL are actually very generically accelerator ready, because they would run on accelerators of any OEM, on NVIDIA, Intel, AMD, all of them can be used. And we have also now HDF5 as our data output format, which is actually forward compatible. That is, as you go in the next few years, that is what everybody will use. And it has actually IO efficiency, which means if you are running a job for about 500 or 1000 cores, then IO will not be a bottleneck, because you are writing files. That will not be a bottleneck. And it's a self-describing format, which means that in future, if you have just found a file, from that you can also find out what does it contain, etc. So it's a very forward-looking format, which we have already started to use in our latest version. Computational complexity is something that can be handled at a very, very high scale by MicroSim compared to any other tool. So think of a 1000 cube domain, so that there are 10 to the power of 9 grid points in your domain, and then several millions of time steps for a reasonable microstructure to come out, and then an n component system, 3 component, 4 component system, and then 3 or 4 phase microstructure. This, if you look at just the multiplication, you would see that it's a humongous task. Okay, and this to be done on a desktop computer, you just forget about it. It's just not possible. It's impossible. And this actually is possible if you combine all the features that I have mentioned before, namely the MPI to split the task across computers, and GPU so that you can do it much faster, and the ability to have scalability, so large number of computations can be done without loss of the speed. So if you put all those things together, a fairly complex task can actually be achieved only by a solver which has the kind of features that we have been able to put. So now that addresses actually one important feature which we have not elaborated in our workshop till now, namely, if you look at what is called the integrated computational materials engineering approach, where we would like to reduce the time scale of development for products, then the so-called vertical integration is very important, where you go from system scale all the way to atomic scale to integrate all the modeling techniques to be able to predict what would happen to the final product, etc. So one length scale at which there is a big problem is the microstructure length scale, because there the microstructure solutions are very, very time consuming. And what we now can say that it need not be a bottleneck. It was a bottleneck earlier. It need not be a bottleneck, because with the kind of scaling that is available, you can actually do it as fast as you have the computational power at hand. Okay, so we end the session by claiming that we are offering a fast, a modern, an open source, and a leading edge set of tools in the form of MicroSim to you, thanks to the project funded by the National Supercomputing Mission, and welcome you to join hands with us and use this tool, which is available at the URL here. And we will hope that many of you would have a head start, so that you could tackle scientific problems without having to do everything from scratch. You can start from where we left the latest version out there in GitHub for you to check out. So with that, I conclude this session, and maybe we can take some questions if there are any to ask. You can unmute and ask. Thank you.
There are some questions.
I will unshare so that.
Okay, no.
Not yet. So if you can't think of questions right now, no problem. You could always put them as an issue on GitHub. You could also drop a line to us. We have all in the website.
I have a question.
Sure.
Yeah, actually, I missed some of the lectures. So my query is, the database, is it also available open source with MicroSim?
Which database are you talking about?
Thermodynamic database?
No. The TDB files, which are free TDB files in the internet, we can actually copy them and distribute because they are free from NIST, for example, or from journals. But the thermocalc databases or Panda databases, they are only meant for those who have bought it. And so IISc has bought many of them from thermocalc, so you will have access to all of them at is a sabotage.
Yeah. And see, they are now hacking the power grid.
Okay. I think we are still connected.
Yeah.
Just a moment. Okay, yeah. Just check. Can you speak?
Yeah, so you can ask questions later too. Okay. So maybe I think another couple of minutes we'll hold on and then we will conclude so that we can wrap up for now.
So, Hari, at some point we will also have similar comparison of code, Wi-Fi code, so that as a comparison with whatever is available.
Yeah, so I can already say that soon a comparison with the Day-2 will be possible because we are writing Day-2 solver with some student there. So we will do it with others also.